All right, in our last section, we're going to be looking at section 6.4, which is called the Gram-Schmidt orthogonalization process. Okay, long name, so we'll abbreviate it to just GSOP. Okay, so it's a process by which we take a set of vectors, a basis, and we make them orthogonal. But we want to cover the same space because we know orthogonal vectors have a lot of nice properties, a lot of good things we can do with them. So we want to be able to use orthogonal vectors. We also know that if I have orthogonal vectors, I can turn them into orthonormal vectors, okay? And so one of the big aspects, I shouldn't say the reason for an orthogonalization process or a normalization process is that we can make some observations here about these orthonormal situations. And so if I have an orthonormal basis, U1, U2, and U3, I'm going to have a matrix U. And this matrix U has columns equal to those vectors, okay? Now, I know if I do U1 times U1, if I do U1 dot U1, that has to be 1 because it's orthonormal, okay? That's what it means to be normal. Same thing for U2 dot U2, and the same thing for U2 dot U3. I'm sorry, U3 dot U3, okay? But then I was thinking ahead here. So, and then my pairs, because it's orthogonal, U1 dot U2 has to be 0, U2 dot U3 has to be 0, and U1 dot U3 has to be 0, okay? That's the nature of being orthonormal. The vectors are orthogonal, so their dot product is 0, and the vectors are normal, so their inner product with each other is 1, okay? Well, that's what it means to be orthonormal. Now, because we know it's orthonormal, if I take U transpose, so I'm switching the rows to the columns, so then my columns then are going to be U1, U2, my rows I should say are going to be U1, U2, U3. Then when I multiply U times its transpose, I'm going across and down. Well, U1 dot U1 is going to be 1, U2 dot U2 is going to be 1, U3 dot U3 is going to be 1, okay? And all of the intermingling, because remember these are vectors, okay? So they have coordinates going down in this case or across in this case. And I'm going to multiply all those. And when I do that, I'm just going to get 1s on the main diagonal with 0s elsewhere because it's orthogonal. Okay? It's orthogonal, gets me the 0s. It's normal, gets me the 1s. Okay? So U transpose times U is equal to the identity. And if it's equal to the identity, then that means U times U inverse is equal to the identity, which is also U times U transpose. So U inverse will have to be its transpose if U is orthonormal, okay? So if the columns of U are orthonormal, that means they're orthogonal and they're normal, then U inverse is equal to U transpose, okay? So that's an important property for us because what we're going to use is we're going to create a matrix factorization. So remember factorization. Okay, we did a LU factorization back in chapter 2. Okay, so we factored into a lower triangular and an upper triangular. Well, our new factorization is going to be a QR factorization. Q then is specifically the orthonormal basis for the columns of A. Okay? So I'm going to take A and I'm going to turn it into QR. I know Q is going to be orthonormal. So then I can multiply both sides by Q transpose on the left. Q transpose Q I know is 1, again, because it's orthonormal, so it's the U in this example. So I can find R then by doing Q transpose times A. And then I will have matrix A factored into two matrices, Q and R. Q, which will be orthonormal, which gives us some nice properties, and R, which will actually be upper triangular, or just triangular, I should say. Most times upper, it doesn't have to be upper, okay? So that's what the Gram-Schmidt process is really useful for, okay? One more reminder here, remember to normalize a vector. To normalize a vector, you take that vector and divide it by its norm. So u1 divided by the norm of u. And remember what the norm of u is. The norm of u is the square root of u1 dot u1. Okay, so just a reminder there, just throwing that back in there, just in case you've forgotten it from previous sections. Okay. All right, so we're going to figure out what the Gram-Schmidt process is here. So I'm going to start with two vectors. Okay. So my vector, my space W is going to be equal to the span of two vectors, and those two vectors are 3, 0, and -1. And the second vector is 8, 5, -6. Okay, so I got these two vectors. Okay, if I look at these two vectors are not orthogonal. Okay, clearly if you do the dot product, you get 24, 0, and 6. The dot product between them is 30. So they're clearly not orthogonal. But I know that I can decompose a vector into an orthogonal component. Right? I can take a projection plus a vector that's orthogonal to that projection and add them together. I can decompose that vector. Okay? And when I do that, I know that the vector y hat would be equal to y minus z, or the vector z would be equal to y minus y hat, either one. Okay, so we're going to use this just like we used it before. So remember what y hat is? Y hat is the orthogonal projection. So it would be the projection of the vector y onto the space W. Okay, and we talked about how to find that pretty extensively in 6.3. So review that material if you need to, because it's going to be very important here in the Gram-Schmidt process. Okay. So when I do that, I'm going to get a vector that's in the space. Okay, vector in the space, and then a vector that's orthogonal to the space. Okay. In this case, z. So in order to get this orthogonal vector, I'm going to name these vectors. This is going to be x1, this one's going to be x2. Okay, so my orthogonal basis now, so we'll call this W star for orthogonal, one. It's going to be the span of two vectors, which I'll call V1 and V2. And we need V1 dot V2 to be 0 because we need those vectors to be orthogonal. Okay, so I can find two other vectors, but the easiest thing to do is say, okay, let me just take the first vector and just keep it. Okay, rather than trying to find two totally new vectors, let me take one vector and find one that's orthogonal to it. Okay. I'm going to take one vector, just make it orthogonal to it. So I'm just going to let V1 then equal x1. Okay. And that's always going to be the first step of the GSOP, which is actually what we're doing here. Okay, I'll explain it in greater detail as we go, trying to get the first examples out of the way so you get a feel for how this works. We're just going to let the first vector be the first vector. Okay, we can do it easily. It doesn't require a whole bunch of extra hoops to jump through and so forth. Okay, now the second vector though is going to take a little more energy. Okay, so V2, I need to get a vector that's orthogonal to this first vector. Okay. But I need it to be in the same space. I need it to be a projection of this second vector. So I'm going to take x2, okay, that would be y in this case, and I'm going to subtract, we could call it x2 hat, or we can call it the projection, right? So this is going to be the projection of the x2 vector onto the v1 vector that I just found, because I need it to be orthogonal to that first vector. So I'm going to do x2 minus, and remember what the projection is. The projection is going to be v1 dot x2 over x. Sorry, I said that backwards. Let me try that again. v1 dot x2 over v1 dot v1. Remember, that's what it means to be an orthogonal projection. Okay, the vector that you're projecting only appears in that one spot. Okay, just to refresh your memory here from the Book's theorem, in case you've forgotten, right? There's a lot of little nuances to this section, so it may take us a little bit. So be patient, take your time. Don't feel like you have to rush through this section because it's maybe the last section, but it's also extremely important. Okay, so you see that formula there for the orthogonal projection. So notice the U1 is on the bottom, and then we multiply it by that U1 vector, okay? So we're projecting it onto U1. In this case, we're projecting it onto V1, okay? So V1 is going to be the vector I'm multiplying by, okay? All right, so we're making progress, okay? All right, so V1 is equal to X1. So V1 is just 3, 0, negative 1. We can just write it down straight away, okay? V2 now, X2 is going to be 8, 5, negative 6, minus, okay, this projection, V1 dot X2. So V1 dot X2. So I've got 3, 8 is 24, 0 and 5 is 0, negative 1, negative 6, 6. Add those together, I get 30. Okay, divide that by V1 dot V1. Okay, 3 squared is 9, 1 squared is 1, so it's over 10. And then we're going to multiply that by the V1 vector, which is 3, 0, negative 1. Okay, so I have 8, 5, negative 6, subtracted. Now 30 over 10 is 3. So I'm going to have 9, 0, and negative 3. 9, 0, negative 3. 3 times 3 is 9. 3 times negative 1, negative 3. Okay, now I need to do the subtraction. So when I subtract 8 minus 9, I get negative 1. 5 minus 0 is 5. And negative 6 plus 3 is negative 3. Okay, so negative 1, 5, negative 3. So here's V1 and V2. Okay, let's check and make sure they're orthogonal. I got 3 times negative 1 is negative 3. 0 and 5 is 0, and negative 1 and negative 3 makes positive 3. 3 minus 3 is 0. So my orthogonal set, okay, and so what is this? This is an orthogonal basis for W, okay? Remember, I had a basis for W, these two vectors, but these two vectors are not orthogonal. So my W star, my orthogonal basis, is going to be this V1 and V2, okay? So W star, let me just summarize our conclusions here. That would be the span, okay? 3, 0, negative 1. And then my second vector that I just found was negative 1, 5, negative 3. Okay, and so there is my orthogonal basis for W. Still a basis for W. Okay, so I don't even have to call it W star. Okay, W star is equal to W because they span the same space. Okay, but now these vectors are orthogonal, which the previous vectors were not. Okay, they're both bases for W. Okay. Okay, now that is an orthogonal basis. So we could also make this an orthonormal basis. Okay, so I have my orthogonal basis. And remember, any linear combinations are still going to be a basis for the same space. So I can multiply these by some constant scalar and still have the same space, same spanning vectors. Okay, so my orthonormal basis, I'm going to need the norm of V1. Okay, so 3 squared is 9, 1 squared is 1. So the norm of that is going to be the square root of 10. I'm going to need the norm of V2. Okay, so V2 now, negative 1, 5, 3. So that's 1, 25, and 3 makes 35. 25 plus 10, so square root of 35. Okay, so my orthonormal basis then, W, will also be the span, okay, of 3 divided by the square root of 10. Well, 0 divided by the square root of 10 is still 0. Negative 1 over the square root of 10. And then my second one is going to be negative 1 over the square root of 35. 5 over the square root of 35. And negative 3 over the square root of 35. So there would be my orthonormal basis. So I have a regular basis, had a basis was just given. I could turn it into an orthogonal basis, then I can turn it into an orthonormal basis. Okay? All right, so we're going to broaden this definition just a little bit. Okay, this will be Theorem 11. Theorem 11 is just our GSOP, our Gram-Schmidt orthogonalization process. Okay, I'm not going to write out those words. It's, you know, a lot of characters in there. Gram-Schmidt orthogonalization process, the GSOP. Okay, so given a basis x1, x2, all the way out to xp for a subspace of Rn. Okay, so I have a subspace of Rn. We're going to have v1 is equal to x1. Again, we just take the first vector. Okay. v2 is going to be equal to x2 minus the projection of x2 onto v1, which would be x2 minus x2 dot v1 over v1 dot v1 times v1. Okay. v3 then will be x3 minus the projection of x3 onto the space, which we'll call w2, because w is just the first two vectors here. Okay. And so when I do the projection onto multiple, then I've got to subtract off both of these. So it's going to be x3 dot v1 over v1 dot v1 times v1 minus, this one's going to be x3 dot v2 divided by v2 dot v2 times v2. Okay, making progress. And this continues indefinitely. Okay, we can do this as many vectors as we need to do it for. Okay, so for example, VP would be XP minus, and it would be the projection, which would be XP dot V1 over V1 dot V1 times V1, XP dot V2 over V2 dot V2 times V2, minus, and then we would continue all the way to a very last one, which would be xp dot vp minus 1, because we would be one short on vectors at that point, time divided by vp minus 1 times vp minus 1, and multiply all of that times vp minus 1. Okay, so that is the Gram-Schmidt orthogonalization process. Okay, it's a little bit tedious, I fully admit. There's a lot of computations that have to be done. Okay, it's not super quick or anything like that. Easy to get a sign mixed up or backwards or forwards, etc. Okay, but you just have to take your time, be careful. Most of the computations are fairly straightforward. It's just multiplication and addition and subtraction. Okay, so if I have a matrix A, this matrix A is 3, 1, negative 1, 3, negative 5, 1, 5, negative 7, 1, 1, negative 2, 8. Okay. So the column space of A covers all three of these vectors, because if I do a row reduction, I just get a nice, pleasant identity set up. Okay, a row reduces to that. So the column space of A covers all three vectors. Okay, and so I'm going to name these vectors x1, x2, and x3. Always good to make sure the vectors are actually independent when you start. Okay, because if they're not independent, then you no longer have a basis. So you can't apply the Gram-Schmidt process to something that is not a basis. Okay, so I've got my vectors. Okay, three separate vectors here, and I want to find an orthogonal basis for the column space of A. So the column space of A covers those three vectors, so I'm going to do an orthogonal basis for it. To do that, I'm going to do the Gram-Schmidt process. Okay, So V1 is going to equal X1, which in this case is the first column, 3, 1, -1, and 3. Okay, that's our starting place. Okay. Put this where we have a nice view of things. Plenty of room to write here. So next we're going to go to V2. Okay, V2. For V2, we're going to do X2 minus X2 dot V1 over V1 dot V1 times V1. Okay. So X2 is equal to -5, 1, 5, -7 minus, okay, X2 dot V1 X2 dot V1. Here's my X2. Here's V1. So -5 times 3 is -15. 1 times 1 is 1, so I'm at -14. 5 times -1 is -5, so I'm at -19. -7 times 3 is -21, so when I put those together, I'm at -40. Okay, so -40. Divide that by V1 dot V1. So 3 squared is 9. 1 squared is 1, that's 10. 1 squared is 1, that's 11. 3 squared is 9, that makes 20. Okay, we're going to multiply that by V1, which is 3, 1, -1, 3. Okay. So I've got -5, 1, 5, -7. Okay. I am subtracting. Okay, this is a -2. So I'm subtracting here -6. -2 times 1 is going to be -2. -2 times -1 is a +2. And -2 times 3 is a -6. Okay. So -5 minus a -6 is really -5 plus 6. So I get 1. 1 plus 2 is 3. 5 minus 2 is 3. And -7 plus 6 is -1. 1, 3, 3, -1. Okay. So let's summarize what we've got so far. Okay. So I have my matrix A. 3, 1, -1, 3. -5, 1, 5, -7, 1, 1, -2, 8. And it's my matrix A. Okay, I have a V1. I've already found my first orthogonal vector. First orthogonal vector was 3, 1, -1, 3. My second orthogonal vector I just found here was 1, 3, 3, -1. Okay, it's never a bad idea to check and make sure those are actually orthogonal. So 3, 3 makes 6, -3 and -3 makes -6. So yes, V1 dot V2 is 0. So those vectors are orthogonal. Okay, so let's go to V3 now. So for V3, we're going to do X3 minus X3 dot V1 over V1 dot V1 times V1 minus X3 dot V2, V2 dot V2 times V2. Okay, so let's write down the pieces here. So V3 is going to be X3, which is 1, 1, -2, 8. Okay, minus X3 dot V1. So I've got my X3 here. 1 times 1 is 1. 1 times 3 is 3. 1 times 1 is 4. 1 makes 4. -2 times -1 is +2. So put those together, I'm up to 6. 8 times 3 is 24. So 6 and 24 makes 30. Divided by V1 dot V1, we actually did in the previous part of the problem. It was 20, so it's still 20. Okay, V2 then, remember, V1 is 3, 1, -1, 3. Okay, minus X3 dot V2. So 1 times 1 is 1. 1 times 3 is 3. That puts us at 4. Negative 2 times 3 is a negative 6, so we're at negative 2. 8 times negative 1 is negative 8, so I am at negative 10. Okay? And divide that now by V2 dot V2. 9, 9, 101 is 20. V2 then is 1, 3, 3, and negative 1. Okay, now I just have to simplify these. Okay? So I've got V3. Oh, that's equal to V3. Let me just write the vectors. 1, 1, negative 2, 8, minus, okay, 3 halves times 3. You're going to subtract 9 halves. 3 halves times 1 is 3 halves. 3 halves times negative 1 is a negative 3 halves. 3 halves times 3 is 9 halves again. Minus the third vector here. So I've got negative 1 half times 1. So negative 1 half, negative 3 halves, negative 3 halves, and a positive 1 half. Okay, so we're almost there. So I've got 1 minus 9 halves plus a half. So minus 9 halves plus a half is going to be negative 3. Okay, minus 9 halves, and you add a half, so you're really subtracting 4. 1 minus 4 is negative 3. Okay, 1 minus 3 halves plus 3 halves. Well, minus 3 halves plus 3 halves is 0, so I'm just left with the one I started with. Minus 2 plus 3 halves plus 3 halves. So 3 halves and 3 halves is 6 halves, which is 3. So minus 2 plus 3 is a positive 1. And then my last coordinate, 8 minus 9 halves minus a half. So 9 halves minus a half is negative 5. So 8 minus 5 leaves us with a positive 3. Okay, so now I have found V3. Well, V3 is going to be negative 3, 1, 1, and 3. Okay, make sure they're orthogonal. 3 times 3, negative 3. 1, negative 1 cancels, plus 3, that makes 9. 9 minus 9 is 0. Negative 3, 3, 3, and negative 3, those all cancel and make 0 as well. So there is my orthogonal basis. Okay, that's the orthogonal basis for the column space of A. So the column space of A had those 3 vectors that were in A here. These 3 vectors will span the same space, but now they are orthogonal. Okay, and similarly, I could find a orthonormal basis. Okay, so the norm of V1 be 9, 9, 1, and 1 would be 20, so it's the square root of 20. And it turns out these are all 1, 1, 3, and 3. So actually all of these are, the norm is the square root of 20. Okay? So an orthonormal basis, then, I would simply divide all of these by the square root of 20. And I could find the matrix Q then. The matrix Q would be 3 divided by the square root of 20, 1 divided by the square root of 20, negative 1 divided by the square root of 20, 3 divided by the square root of 20. Second column, 1 divided by the square root of 20, 3 divided by the square root of 20, 3 divided by the square root of 20, negative 1 divided by the square root of 20. Fourth column then is going to be negative 3 divided by the square root of 20, 1 divided by the square root of 20, 1 divided by the square root of 20, and negative 3 divided by the square root of 20. Sorry, that last one is positive. Only made one sign mistake there right at the very end. Okay. So that'd be my matrix Q. So I could find R by doing Q transpose times A. That would give me my matrix R. Okay. Now notice that you can always multiply by a scalar. In this case, we divided by a scalar, and we still had orthogonality. You can always multiply by a scalar and keep it orthogonal as long as that scalar isn't 0. Okay, if that scalar is 0, then you don't have a basis anymore. You do still have it orthogonal, but you won't have a basis anymore because everything is orthogonal to the 0 vector, but the 0 vector is always a dependent set. Okay, so keep those factors in mind. Okay. All right. So next example here. So I'm going to have x1 is going to be equal to 1, 1, 1, 1. x2 is going to be 0, 1, 1, 1. And x3 is going to be 0, 0, 1, 1. Okay? These vectors are clearly independent, but they are not orthogonal. So I want to make them orthogonal. Okay, so as always, we're going to use the Gram-Schmidt process. And the first vector, we're just going to keep 1, 1, 1, 1. Okay? So now we go to our second vector. Find v2. We are going to do x2, which is 1, 1, 0, 1, 1, 1, minus, okay, this is going to be x2 dot v1 over v1 dot v1 times v1. Okay, so I'm going to have 0, 1, 1, 1, minus, let's do the dot products here. I'm going to have x2 dot v1. So that's 1 times 1, 1 times 1, and 1 times 1. I get 3 over v1 dot v1 is 1, 1, 1, and 1. Those together makes 4. Okay, and we're going to multiply that times the v1 vector, which was 1, 1, 1, 1. So v2 will equal 0, 1, 1, 1 minus, I get negative 3/4 all the way down. Okay, so 0 minus 3/4 is a 0 minus a negative 3/4 gets me a positive 3/4. 1, sorry, I brought that negative sign inside. Let me try that again. There we go. So I brought that negative sign inside. It's going to be negative 3/4. Okay. Second one, then I'm going to have 1 minus 3/4. That's going to be a fourth. 1 minus 3/4 is going to be a fourth, and 1 minus 3/4 is going to be a fourth. Again, be very careful about your positive and negative signs. Okay. You saw me basically make a mistake right there. I brought that negative sign in here, so it's going to be plus on the outside. If you keep the negative outside, then these would all be positive. Okay. Think of it that way as well. Let's make sure these are orthogonal. So negative 3/4 times 1 is a negative 3/4. And then a fourth, and a fourth makes a positive 3/4. You put all those together, you've got your orthogonal second vector. Okay. So let's recap what we've got. We've got v1. All right, fighting the camera a little more today than some. 1, 1, 1, 1. v2 now we just found is negative 3/4, a fourth, a fourth, and a fourth. Okay. Now, we'd really rather not deal with all those fractions if I can help it. And we know that multiplying by a scalar keeps us as having an orthogonal vector. So I'm going to take v2 and multiply it by 4, and that's going to give me negative 3, 1, 1, 1. And that's a lot easier vector to deal with. And it's still orthogonal to v1. So I'm going to just replace v2 by multiplying it by 4, because it's going to make my computations easier later. Not doing all those fractions in the dot product will just be easier for us to take on. Okay, so I'm actually going to scratch v2 and turn it into my new v2, which is actually just 4 times it. Okay, so v3 now, we're going to do x3 minus x3 dot v1 over v1 dot v1 times v1 minus x3 dot v2 over v2 dot v2 times v2. Okay, let's remember what x3 was. x3 is 0, 0, 1, 1. So v3 is going to be 0, 0, 1, 1 minus, okay, x3 dot v1 is 0, 0, 1, 1. That's 2. v1 dot v1 is still 4. v1 then is all ones minus, okay, x3 dot v2, that's also 2 because I'm going to get 0, 0, 1, and 1. Okay, the denominator here, this is going to be 3 squared is 9, 1, 1, and 1, so that's 12 times the vector, negative 3, 1, 1, 1. Okay, and again, I'm trying to take it piece by piece here because I know there's a lot of arithmetic. There's a lot of opportunities to goof up. So minus, it's going to be minus a half, a half, a half, and a half. Okay, minus, okay, 2/12 is 1/6. So 1/6 times -3 is -1/2. 3 divided by 6. Okay, then I have a 1/6, a 1/6, and a 1/6. Okay. So I have -1/2 plus 1/2. -1/2 plus 1/2 plus 0. That first coordinate is 0. Okay, 0 minus 1/2 minus 1/6. So 1/2 would be 3/6. Another 6, that would make us at 4/6, but negative, so it's -2/3. Okay, 1 minus 1/2 gives us a positive 1/2 minus a 6. That's going to be a positive 1/3. It'd be 2/6. Okay, and then I get the same thing for the last coordinate. Okay, and again, I'm going to multiply this by 3. So I'm going to do 3 times V3. That's going to give me 0, -2, 1, and 1. So I've got my set now. Okay, so my basis for W is going to be the span of 1, 1, 1, 1, -3, 1, 1, and 1, 0, -2, 1, and 1. Okay, now let's make it an orthonormal basis. So the norm of V1, okay, is going to be the square root of 4, which is 2. The norm of V2, this would be 9, 1, 1, and 1. It would be the square root of 12, which is 2 square roots of 3. Because it's 4 times 3 is 12. And the norm of V3, okay, is going to be 0, 4, 1, and 1. That's the square root of 6. So there's not much else we can do with. So my orthonormal basis, which we know makes up the matrix Q, okay, is going to be 1/2, 1/2, 1/2, and 1/2. Okay, because I took all the ones and divided them by 2. I'm going to have -3 over 2 square roots of 3, 1 over 2 square roots of 3, 1 over 2 square roots of 3, and 1 over 2 square roots of 3. And then my fourth one, I'm going to have 0, because 0 over anything is still 0. -2 over the square root of 6, 1 over the square root of 6, and 1 over the square root of 6. Okay? So our last task then is going to be to find R. Okay, find R. So to find R, we need to do Q transpose times A. Okay? So let's write what Q transpose would be. So we turn the rows into the columns into the rows. Okay? So I get a 1/2 going across the top row. -3 over 2 square roots of 3, 1 over 2 square roots of 3, 1 over 2 square roots of 3, 1 over 2 square roots of 3. Bottom row then is 0, -2 over the square root of 6, 1 over the square root of 6, 1 over the square root of 6. Okay? Now I'm going to multiply that by the matrix A. Now the matrix A, remember, is your original vectors. So your original vectors were 1, 1, 1, 1, 0, 1, 1, 1, and 0, 0, 1, 1. Okay, so you can see I have the same number of columns in the first that I do rows in the second. I can go across and down. Okay, fortunately, all the numbers in matrix A are ones. Makes it easy to deal with. So going across, I've got a 1/2, a 1/2, a 1/2, and a 1/2. It goes together to make 2. Okay, second row, first column. -3, 1, 1, and 1 is going to make 0 no matter what the denominator is. So I've got 0. Okay, bottom row now, 0, -2, 1, and 1. That's going to make 0 again as well. So you start to see this triangular setup form for R. Remember that this is going to give us our matrix R. Okay, so it'll give us a factorization of A that includes an orthonormal basis. Okay, So I go to second row now, second row, first column. I've got negative 3 times 2 squared root of 3. Oh, sorry, 0. Then I've got 1, 1, and 1. Okay, so 3 over 2 square roots of 3. Sorry, I got ahead of myself there. That is the second spot. That was second row, second column. So first row, second column is going to be 0, a half, a half, and a half. That is 3 halves. There we go. So I wrote it almost in the right place. So first row, second column, 0, a half, a half, a half, makes 3 halves. Second row, second column, negative 3, 0, 1, 1, and 1 is going to make 3 over square root of 2. Okay. Then third row, second column, 0, negative 2, 1, and 1 makes 0 again. Okay. And our hardest one is going to be our third one, which is going to be 0, 0, half and a half makes 1. 0, 0, 1, and 1. So I'm going to get 2 over 2 square roots of 3, which we actually could simplify by dividing the 2's. I'd get 1 over the square root of 3. And then the third row, third column, 0, 0, 1, and 1. So I get 2 over the square root of 6. And there is my matrix R. Okay? Well, it's an arduous process. It's not quick. I wish it was, but it's not. Okay? Take your time. Go slow. Be careful, and you will get there. Okay? All right, so that's going to end our 6.4 video, okay? I'm going to make one more video that's going to be another example of the Gram-Schmidt process, okay, along with finding A, Q, and R. Just going to have one more example, so it'll be called the 6.4 extra example. Okay, so you can use that video if you need another practice example on this information in the Gram-Schmidt process. But it's a fairly straightforward algorithm that just takes a lot of patience and a little bit of time and arithmetic, okay? It's fairly straightforward. We don't really use anything super new to what we've done. We're still doing matrix multiplication, dot products, orthogonality, normality, the norm, all of that, okay? So there'll be one more example that'll be in the next video, right? It's optional, but if you need that extra practice, please take a look at that video. And I will see you there. Have a good day.